So, problem 3.2. Consider a survival function. So it's very nice, this problem. They say assume that alpha is greater than 0, assume that beta is greater than 0, and look at this survival function where the exponential is taken to the minus beta times t to the alpha power. And then they ask us to, well, find the value of the parameters that satisfy this and this. So let's just take a look at that. What do the mu's stand for? Well, they stand for mortality intensity. So mu, the mortality rate, or sometimes in this chapter they just call it intensity, sometimes they call it mortality rate. Sometimes they might even call it hazard rate, but all in all, we know more or less what this means. Mu, the mortality rate, is the intensity of imminent death at time t, given survival up until time t. So what do we have here? We want to find alpha and beta such that the mortality rate satisfies two equations given the survival function. So we know F bar, hence we know mu, at least in terms of at least in terms of alpha and beta. Since, well, both in chapter 2 and 3, we know that the survival function can be expressed using the intensity function as e to the minus integral from 0 to t mu of s ds. And I think I'm trying to write t inside here. So correspondingly, the mortality rate, or the intensity function, potato potato, is equal to the minus derivative of the logarithm of the survival function evaluated in t as such. And that means that we are able to find the mortality rate here. So what do we have? Well, we know that f bar of t is equal to the exponential of minus beta times t to the alpha. Hence, using this, we know that the mortality rate, mu of t, is equal to minus the derivative of minus beta t to the alpha, because I take the logarithm of the exponential and that just cancels out with each other. And this is equal to beta times the derivative of t to the alpha. And this is very, very nice. This is very, very nice because this just gives me beta multiplied by alpha times t to the alpha minus 1. So now I know what mu is for t greater than 0, presumably. They don't tell us anything about t being greater than 0, but the intensity only really makes sense when we look at non-negative random variables, and also when we consider lifetimes, it also only really makes sense to consider non-negative random variables. So now we want to find alpha and beta. So what do we know? We know certain things. we know that mu of 40 is equal to 4 mu 10. So alpha and beta should satisfy this. Also, alpha and beta should satisfy that mu of 25 is equal to 0.001. So mu and beta should satisfy these two conditions 1 and 2. And also, we know that in general, mu of t has the expression beta times alpha times t to the alpha minus 1, which was what we found out just earlier in this exercise. So we know the following. So hence, we must have that the first condition implies that beta times alpha times 40 to the alpha minus 1 is equal to 4 multiplied by beta times alpha times 10 to the alpha minus 1. And this means, well, let's take a look at this. The beta and alpha cancel out, and I can divide the 10 to the alpha minus 1 over here, in which case I will have 4 to the alpha minus 1 is equal to 4. And this quite clearly points out to me that alpha minus 1 should be equal to 1, because you can't take 4 to any other power that just results in 4 being itself. So that means that alpha is equal to 2. So that part is done. Now I look at 2, which implies that beta times alpha times t to the alpha minus 1, where t is equal to 25. So beta times alpha times 25 to the alpha minus 1 is equal to 0.001. Now, what does this give me? Well, I know that alpha is equal to 2, right? So I can at least plug that in. And that gives me that that beta times 2 times 25 to the first, so that's beta times 50, is equal to 0.001. And that gives me that beta is equal to 0.001 divided by 50. So all in all, I have found out what beta and alpha should be for the above assumptions of the mortality rate to hold true. Now, why do we do this? The reason why we do this is because often it's actually easier to estimate the mortality rate than it is to estimate a survival function. There are certain methods of estimation that you will not learn during this course, but just very roughly, we can kind of estimate the mortality rate using one of those. Look at the ratio between how many people have died and how many people we've observed, all in all. So in general, it's quite easy to come with statistical conclusions about the mortality rate compared to how it is to look at density and so on. So in this case, yeah, this is one of those cases where we estimate the parameters using the mortality rate. And we found out that the parameters were respectively alpha equal to 2 and beta equal to 1,000th divided by 50. And you can find the value of that on your own. See you in the next exercise.